East, Universal is here,
Around
Mutadisa
5.
is here, Richard is here. Okay, Praveen is here. Okay, okay. Should we start or should we wait for a few more minutes for the others to join?
We'll give few more minutes, sir.
Okay, okay. Okay, by the time we come to the main subject, so let me ask, how many of you have good idea about quantum mechanics? I guess everybody has gone through this quantum mechanics at least once in his or her lifetime. That is that right? At least it was there in any of the curriculum.
Not in detail, but somewhat high level. I know IBM is doing Qiskit
Mhm.
summits and Qiskit meetings and all. So I had attended couple of, which I did not understand actually.
Yeah, I'm not asking about quantum computer, but I'm asking about quantum mechanics.
No, sir, we have just heard
No,
about
no,
it.
totally forgot. Quantum computing a bit I know.
Okay.
Mechanics is difficult to remember actually now. Recollect.
Yeah, it's difficult to remember, but do we remember what exactly it is? Like if all the classical mechanics, the Newtonian mechanics, the laws of motion, force, acceleration, mass, everything was working fine for us. We could create steam engine. We could create steam engines or machines. So we could run vehicles like the motor cars. Everything was fine. Everything we could do with normal mechanics or the Newtonian mechanics or classical mechanics. Why did we need something called quantum mechanics? And what problem did it solve? Like why the scientists came up with another crazy idea called quantum mechanics? Because the mechanics we knew before quantum came, that perfectly was working for us. We could do lot of things. Steam engines were there. The factories, we could set up factories, we could create machines, we could build a lot of other things. Everything was perfectly fine. So why did we need quantum? Any idea on that? At least that, not detail on the quantum mechanics.
I mean,
Whatever.
in traditional electron, proton, neutron was there in all the things, but I think quantum is giving some new dynamics apart from these three properties. I
Okay.
don't know the actual thing, but yeah, it is apart from something proton, electron, and neutron.
Okay. Yeah, that is one thing. One way of explaining it that I used to think when I was a kid, not a kid, but in my college when I first started reading this quantum mechanics. One of the reason I always thought that these scientists are crazy people. They don't like anything simple. Rutherford's electronic model was perfectly fine, and they unnecessarily make it complex. The mathematicians and the scientists, they are very good at making anything very complex. That is one of the reasons they love to make everything very complex. And quantum mechanics, the formula and whatever we have learned was kind of out of our uh, bandwidth, right? So that is one way of explaining that. Another one that the one that Parth said, that there might be some things which we could not explain using the traditional mechanics or classical mechanics. But what are those things? We could explain our world. We could explain the way machines work. We could explain the way anything is in motion, anything is in race, how we can explain that, how the motion will create, how the force will act, everything we could explain. But what are the things that we could not explain with classical mechanics? Any idea?
Classical is usually on a high level, no? Means quantum is somewhat deep, granular level.
Okay, I will come to that.
Okay.
Before coming to quantum computer, we just little bit we can brush up our memory of quantum mechanics, because this quantum computer is built on that quantum mechanics, and quantum crypto systems are built on quantum computer. So let us start from the very beginning. Quantum mechanics. What quantum mechanics means? This is like okay. I was talking about Rutherford. Rutherford given a very nice atomic model that says that there is a proton and a neutron in the center of a atom, which we call nucleus, and the electrons rotates around that nucleus. All those protons and neutrons, that is together, they are forming nucleus, a small center, and and around that center all the electrons are rotating. That is perfectly fine, that is how we can see our world. But the problem is when scientists went deeper and deeper and deeper into the atomic system, they found some crazy things. They found the normal mechanics or the normal laws of motion, the way we see the force is not working the way we always see or the way we explain it. That means we know a simple formula, force equals to mass into acceleration. But inside the atom, when they went deep inside the atom, they found these small particles, electrons, protons, neutrons, they are not following the same rule. They are following something completely different. No, there is not force equals to mass into acceleration. There is force, but that force works completely different way, and that grew up their brain. What it is. So all the rules that we have learned for our world or in our universe, what we see around us, those those laws or those laws of physics do not hold good for the small particles. One of the very nice explanation of this is probably this is the first experiment that proved that inside the atom, our normal understanding of physics is not working. So this is a simple experiment. Let me change the color. You can see my screen, right? See,
Yes.
Yeah.
just think there is a wall, and this wall has two holes. This is a hole or slit. I shouldn't say hole. It is a slit, and there is another wall in the another wall in the background of this wall. So this is one wall with the slit, and there is another wall in the back. Imagine you have a gun. Okay, and you start firing on this direction. right? So what will you see on this, on the second screen? This is first screen, this is second screen. What will you see on this second screen? Where the bullet holes you can see on this screen, on this wall, second wall? Any answer? Where will you see the I
On
guess
the slits, this the space left.
this place you will see there are a lot of bullet holes. And here in this place you will see lot of bullet holes, right? Rest of the area in this wall, second wall will be clean. There will be no bullet hole. Only the bullets that passes like this. Only the bullets that passes like these. Maybe few bullets will go like this. Here also. Rest of the bullet will be blocked by the previous wall, right? So maybe this is the area where you will get bullet hole, and this is the wall where you will get the bullet holes. Rest of the places on this second wall, you will not see any bullet holes. Now they perform the same experiment with electron. What did they see? Do you remember? These things probably we all of us have read it. Now we are doing the same experiment with electron. So again we have another second wall or second screen actually. Here we have a first screen with the slit, and we send lot of electrons. Do you say do you understand or do you remember what happened in this second screen where maximum number of electrons we could find in this screen? In this area. This area. There is no way of doing that, right? The particles are going that should come in this area and this area. But here there is no way of an electron to pass, but they found there is a maximum number of electrons. In fact, when they draw a graph that how many electrons is hitting where, they found this is kind of something like this. So here maximum number of electrons. So here maximum number of, if we just count how many electrons has hit here and we can just make a frequency analysis of that, we will find like this. Very strange, right?
Yes.
So the explanation is like this. Then scientists thought that okay, our normal understanding of the particle is not working. So they said something called particle wave duality. Why so? Because this kind of thing we have seen in one place, another place where in wave. Just imagine instead of the electron and instead of this wall and state, just imagine you are doing it on a lake or a swimming pool or a pond, and you are doing the same thing. There is the one wall with the two slits, and it is a vertical wall inside the swimming pool, and you are dropping some stones on that. You are constantly dropping some stone here, and there is a wall with two slits and another wall here. How the wave or the ripple in the water will form like this, right? This will happen, right? This is how the ripples will form. And from here, the ripples will not pass like this. It will again form like this. right? This is how it will happen. We understand it, right?
Yeah.
Yeah, it's like a sound wave.
Just like a sound wave or any wave. So I'm taking an example of ripple in the pond. Probably everybody of us will correlate with that, or everybody of us can connect with that. Yes, sound wave also will be like this, or say any wave will be like this. And if it happens, just see in this area where the maximum number of electrons we got, that area there are overlapping of two waves, and that's why in this area there will be maximum number of ripple you will find, or in case of electron there is maximum number of electrons, or if it is a sound wave you will actually find in this area maximum number of maximum decibel you will find here, maximum sound will be captured at this place. If it is light, maximum light it will come. You can think of another example. You are inside a dark room. It is completely dark, and one of the if you just put two holes in one of the wall, what you will you see? If you just turn back, you will actually find, uh, if these holes are reasonably big enough, you will find actually the opposite wall of this. So this wall here, the center will be maximum illuminated. Got it? Or
Sir,
just
in the waveform which you explained, but it still doesn't make difference, right? So the as you mentioned, the wave, if you look into the diagram,
yes.
uh, the concentrated place, the wave is not even hitting. How can they say that that is where the maximum happens? There is no
No,
contact.
there is because wave will come like this, because there is a maximum superposition, because two waves, if you just add two waves here, you can see two waves are adding up, right? At this area, there are two waves are adding up. That's why here you will get the maximum number of waves, or maximum, I would say maximum energy will find here. Here at this area, just one wave is hitting. Here also one wave is hitting. But here, two waves adding up, and it is that added wave or superposition wave
The
is hitting,
overlap.
is the overlapping, yes. In wave, we call it superposition, but it is overlapping, nothing but the overlapping of two. Due to that overlap of these two waves, we will get maximum number of energy at this point.
So, is this used in LED TV or a CRT tube kind of technology, backlit LED and all? Anything related to that?
I don't know exactly whether this is the one or not, but yeah, if you can think of two lights, you have added two lights in the same wall, and in the opposite wall, you will actually find the maximum brightness on the opposite wall, exactly the place which is in between these two lights. Is not it? Because that area is getting light from both the lights.
Hmm.
That's it. So this is how the scientists explain the phenomena. Like when we did it with the electron, though we thought electron to be a particles, but it is actually acting like waves. That's why they said electron is not just a particle, but also it is a wave. And that blew up the minds of all the scientists, because that was very new for us, or new for all the scientists that time. Oh, what is that? It is particle. You are saying particle. Sometimes you are saying it is wave. अरे बोलना क्या चाहते हो? I mean, कहना क्या चाहते हो? So that's kind of question. Whether just tell me it is either a particle or it's a wave. But this is the scientists explain it in this way. No, this is at the same time. This is a particle and a wave, and it will follow both the physics. The physics related to particle, yes, it will follow. The physics related to wave, that also will be followed by this electron. And when it will follow the particle, physics, we do not know. When it will follow the wave physics, we do not know. But at some point of time, it will show you as if it is a wave, and some point of time it will show you some evidence that it is a particle. That's something that started our quantum mechanics or quantum physics. So when we go deeper inside an atom, the world inside or the universe inside that small world is completely different than the world we see. There, our laws of physics are not working. If we needed some completely new physics or some completely new laws of physics to explain those phenomena that is happening inside an atom, and that is why that is what we are calling quantum physics. Clear? Now we are coming to the quantum computers. So I guess now we all understood what is quantum physics, right? There is no confusion.
Yes.
Okay. Now, what is a computer, a quantum computer? Now, crazy people are always there. Crazy scientists are obviously always there. So, in 1930s, there were a lot of crazy people like Heisenberg, like Niels Bohr, who came up with this particle wave idea, the probabilistic approach of probabilistic position and momentum of electron. Okay, that is something I have missed. Probably that is one another very important aspect of quantum physics that we will use in quantum computers. That is where rather in the Rutherford's model it is very nice. It is nuclear, and around that there will be electrons. There will be different orbit and different electrons. From here, Niels Bohr said, where you will find the electron? They are rotating like particle, they are rotating like wave, but where exactly we will find the electron? Where is that electron? And also these electrons has some spins. It is not only rotating like this, but also these electrons, if we go to the if this is a particle electron, then it also rotates like this, either like this, or some of the electrons are rotating like this. Some of the electrons are rotating like this. Okay. So on some of the axes, any of these axes, like if this is a particle, this is a small particle, we do not know where is that axis. We really cannot find, but there is some imaginary axis on around this axis. This particle is rotating. That is what Professor Niels Bohr said. And this might be like this, or this might be a slant one. This might either rotate in this direction or it might also rotate in this direction. We do not know the rotation. We really cannot find. And Heisenberg said something more. He said it is not only rotating, we do not know where it is, which direction it is rotating, where is this axis, where the electron is located, we really do not know. And the funny part is, it is not only we do not know, but also it is actually happening all possible things. That means it is the same electron is rotating around this axis, the same electron is rotating around this axis, the same electron is rotating around this axis. We cannot find which axis it is rotating. That is one thing. But something that we really cannot understand with our knowledge of our physics or our universe, that it is not it we always think it will always be in one single state. Either it is doing this or it is we always thinking like this, either or. But Heisenberg said no, in quantum level it is not or, it is and. It is rotating like this as well as it is rotating like this, as well as it is rotating like this. This is all and. which we really cannot see anywhere in around our world. How it is possible, or where the electron is located. We think either if there is a circle or a sphere maybe. Just let us see, there is a sphere. So we think electron is either here or here or here or here somewhere around this sphere. The electron is we can find the electron. That's how we think, right? Again, Heisenberg said no, not like that. The electron is actually everywhere. The same particle, it is actually everywhere inside this globe. It's not like only here or only here or only here. It is everywhere. Just the way we explain waves. Waves are everywhere. We really cannot say that wave is at this very particular point. The wave, we cannot find the location of the wave. It is everywhere. Similar to that, this electron is actually everywhere. It is here, 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 here. But the moment you measure it, the moment you are capturing or you are measuring the position of the electron, that moment it is at particular one point of this. No, but actually, when you are not measuring, it is everywhere. And they said it is where this electron is located. For that, he has given a formula. It is always kind of a probabilistic approach. So just in a 2D space, not in the 3D space, just in the 2D space, in a coordinate geometry, he said this electron can be anywhere on this area, anywhere. We think about anywhere. He said it's not anywhere, it's everywhere, which is very difficult for us to understand what is everywhere. And he says at any point of place, whether you will find the electron or not, that is dependent on the probability. So everywhere, whether I will find it at this x and y position location, he says we will represent it as probability of x and y. So this is the location of any electron. Where this electron is located, it is at any point, at any space in this 2D area, will define it as a probability of getting that electron at this space. Some of the in different orbit, actually there are p orbit, s orbit, so different orbit looks like differently. Some orbit says the electron is something like this. That means in this area there is a maximum probability of getting an electron. This area there is maximum probability of getting an electron, but in this area there is lesser chance or lesser probability of getting an electron. Some of the cases it is just around. So everywhere it is equally distributed. Everywhere you can find the equal probability of getting an electron. Sometimes we can say this is like it's something like this. So different graphs we can draw here, but the point here is where you will get an electron that is dependent with a probability, and that's how we represent a position of an electron, or not electron, proton, neutron, all these small particles. So all these things we can find inside a cloud of 3D space. Here I am explaining it with a 2D space, but actually it is a 3D space. Inside that 3D space, where we will find the electron, that depends on a probability. We can just find the probability where I can get it. That does not mean that it is there, or that doesn't mean that when you are measuring, will find the electron at that very particular point. But there is a probability how much you can what is the probability, or how much chance you have that you will get the electron here. But you cannot say that electron is actually here. Makes sense? Now let us come to quantum computer. This thing gave another wonderful idea to the mathematicians in 1980s, 1970s, 80s, when the computer was coming, we knew how we can do the computations with the machines. We already knew that. That time some scientists thought, how about applying this idea into a computation? How is that possible? Okay, instead of bit, what we are using as a register, instead of a bit, how about using electrons, the position of the electrons as the information? Because it is all about information. Why we are using bit? It is either zero state or one state, or in an electronic circuit, it is either off state or on state. Now the scientists thought this is our normal physics. This is how we see it is either on or off. Now in the quantum world, it is different. So in the quantum world, it is on and off simultaneous. If that is the case, then we can actually, instead of having a circuit which is in on state and off state, we can actually use the position of the electron as a source of information. How will that work? So this particular register, quantum register, 1, 2, 3, 4, 5, 6, 7, 8. A quantum register of 8 bit. Normal register, sorry, this is a classical register, it either 0 or 1. 1, 1, 0, 1, 0, 1, 1, something it is written, just a random number. But in quantum, it will be 0, again it will be 1, same thing. So it is one register, but it is actually holding all the possible values that we can create with zeros and ones, 8 zeros and 1. So if it is one bit of quantum flip-flop, that means it is 0 as well as it is 1, anything. So how will that work? Just imagine a filter. So this is like, maybe as I said, it is this is an electron, small electron, and it is, say, rotating like this. And this is another electron. This is, say, rotating like this. One is clockwise, another is anti-clockwise. So we can imagine that if the electron is rotating, clockwise, then we'll say we'll define it as 1, and when it is rotating anti-clockwise, anti-clockwise will be 1 and clockwise will be 0. That is one way of representing 0 and 1. That's fine. They thought clockwise means upward arrow, anti-clockwise means downward arrow. Fine. And this electron, this particular flip-flop, is either, we always think it is either rotating this direction or rotating this direction, or this either this or this. But actually, it is both. It is both rotating clockwise, both rotating anti-clockwise. Exactly the way quantum physics explains. In that case, the same flip-flop can be 1, can be 0 with the probability. So the probability of being 1 will denote as P1 1, and it is P2 0, something like that. So it will be either 0, either 1. And how we will operate on this? We'll have filter. If we can filter out these P1 filters, like all the probability where it will be 1, all the probabilities we can add up, then we can create a filter which will filter just 1 for me or 0 for me. I'm giving another example which will make it a little bit clear to you. So far, I think probably I'm successful to confuse you a lot so far, if I'm not wrong. Okay. This flip-flop. Okay. Okay. One quantum filter that I was talking about, probably I'm unable to express it in words. One of the quantum filters we use in our everyday life. Do you know what is that? Is the polarizer. It is a polarized sunglass. Okay. What it does is a wave of protons. Wave of photons are coming here. Light wave is nothing but waves of photon, and it actually filters out some of the photons and it lets some of the photons in. What photons it will let in? It is the same thing. Photon, if you just think about, say it is a photon, some of the photon particle is, say, this is how the photons are coming as a wave. Some of the photon particles are exactly perpendicular to the direction. So if this is the x, but this is the axis, then some of the photons will be perpendicular. It is exactly the perpendicular. It is rotating perpendicular to this. Some of the photons, like this photon, can rotate like this, or this photon can rotate like this also. So what this filter does, you can see this photon. So this photon is, we can say this is perpendicular. This is like this. So this is the direction of the photon. This is the direction of the photon. The way it is rotating. It doesn't mean that physically which direction it is moving. The photon is moving towards one single direction, but the direction what I am talking about is the spin of the photon. Every particle is spinning around an axis. So but what happens, the perpendicular spins, some of the spins or just the perpendicular spins, it just filters out. The photons that is rotating around the horizontal axis, it just lets that those photons in. Rest of the photons, it just filters out. That's why we see differently, because some of the light sources, some of the light waves are not getting inside of our eyes. That's how a polarizer works. This is nothing but a filter. It filters out some of the rotations or some of the directions of the photons, right? Now we understand what a filter works like. This is a filter. Now the problem that I was explaining before, the same photon might rotate around this axis or this axis. This is not either or. We are creating the either or condition using the filter, but actually in reality it is both rotating this direction and this direction. But at the moment the polarizer is applied at the very point of time, we will filter out one of these rotations because it is doing both the direction it is moving. We are only filtering out one of them, and we are letting just this direction. Now is it clear? A little bit clear.
Yes.
Yes में दम नहीं था. Okay. Yes.
Polarization is clear,
Okay. But
but
what?
how we are correlating with the register?
Okay. When polarizer filter is working, say this is a polarizer filter, PA, how it is working, it is actually taking a quantum particle. Photon is a quantum particle. We understand that this is a wave, this is a quantum particle. Photon is very small particle. It does not follow the normal rules of physics. And at the same time, a photon can be like this or can be like this. This means this equals this actually means so many symbols. This means the photon. This is a photon. This photon is rotating like this direction or this direction. So perpendicular to the particle axis. And this means this photon is rotating this way. That means it is rotating around the horizontal axis. Fine. In the quantum physics, the same photon is rotating in the both directions. So the photon is in this direction, the same photon is in this direction, the same photon, both directions. What this PF does,
So a
PF,
total four combinations
yes,
in one
so
direction, two combination.
yes, actually not four. There are infinite combination because this is not like this. This is like this. This is like this. This is like this,
Okay.
and this is on the 2D space. Now imagine in the 3D space. It is actually in every direction. What this polarizer filter does, it filters out one particular direction, just all the photons that is rotating around this horizontal, either this direction or this direction. It is only taking this horizontal ones, and it is cancelling out the verticals. Okay, so this
Those are the UV rays, which
those
it
are,
is cancelling out.
it's not only it is not a UV filter, is not a polarizer filter.
Okay. So
Polarizer filter is different. It only lets you in which is not directly coming to your eye. So this photon will actually hit your eye directly. That's why your eye will get irritated. So if it just cancel out this one, then rest of the direction of the photon is fine for your eyes. You will not get irritated. You will see everything. Got it? That's why if you use a polarizer filter during your driving night, you will see the difference. But don't do that because it is since it is a black screen, your visibility will anyway very less. But when the light falls on the perpendicular to your eyes, so not perpendicular, horizontal to your eyes, you will not you will not feel like what is that term, like the when the other headlight falls on your eye, it's very
yeah, got it.
Glare.
yeah, clear. So it will not give you that clear.
And any light which is horizontal would be cancelled out.
Exactly. So this is what polarizer filter does. And in quantum world, we can say this polarizer filter is actually breaking down the quantum nature of this photon and filtering one of them. So what it is doing, it is actually breaking quantum nature. So now it was in all direction. Now it is actually breaking into multiple different directions. So it has some of the photon has a probability of this going this direction with P1, going this direction as P2, going this direction as P3. Something it is just broken down that those photons, because one photon has all the direction. What this does in quantum world, it actually breaks the quantum world, or it breaks down the quantum nature of the photon, and it does some operation and then again send it as a particle wave, or it again sends as a quantum particle. So this, for working this polarizer filter, it has to break the quantum nature of the particle. Otherwise, it cannot filter out, right? So that's why this polarizer filter is actually a quantum filter. Now, when we use a polarizer filter, the people who is building the polarizer filter, they do not know what is happening as a quantum level or not. But it is in the logical state, in the logical thought exercise, we can think that polarizer filter is nothing but a quantum filter, or what it does, it actually breaks the quantum nature of the photon. But when somebody invented polarizer filter, he did not thought about that. He just saw that okay, light is passing, and this is something which is blocking some of the lights. It is good for our eyes. But that is a naturally found filter, or we have created some filter which is working in the quantum level. Got it? So this is a filter which actually filters out one photon or one quantum one Like it filters out one quantum particle, or it filters out one quantum what preposition I would say. But anyway, it is actually taking, it is converting the quantum into the normal physics and then does some operation on that and then again send it back as a quantum physics. Fine. This is how we can, it's oversimplified, but this is how it we can start thinking on that. Now if you really want to go deeper into the quantum physics, then or quantum computation, then probably this is a very niche statement, but we can think in this way. So just like a polarizer filter, just imagine there is a flip flop, quantum flip flop. Flip flop means it is either 0 or 1. That's what we thought. Now the quantum flip flop says it is 0 and 1 together, it will be here. And how we can express that? So this particular flip flop has a probability, some P1 probability of being 0 and some P2 probability of being 1. The same flip flop. Now we have, just like a polarizer filter, if we have a filter, something like quantum computation filter, something like that, if we have, then it will either filter out this P1 or P2, or it either will filter out this 0. If we have a P1 filter, it will filter out 0. If we have a P2 filter, it will filter out 1. And this we represent as a quantum bit. And this is nothing but this is nothing but representation of a quantum bit. Don't get scared with this notation. This notation means it is a quantum bit, or if it is a bit, we usually write a bit like normal bit, we can write like b. If it is a quantum bit, we represent it with this bracket. Okay. And a quantum bit means it can be both in 0 and 1 position. Some of the cases it is 0, some of the cases it is 1. And we have a filter. If we can create a good filter, we can filter out whether we want a 0 or a 1. What is the implication? Say we take a 2-bit, 2-bit quantum computer, 2-bit quantum computer. So in normally we have either 0, 0 or 0, 1 or 1, 0 or 1, 1. Any of these values we will see in a particular in a classical register, right? Or a classical computer, it will be either of these, any of these 4 combination, any of these 4 will be there. It's fine. And if we want to search whether this is this this particular number is here or not, we just want to know there are 4 numbers we have and we want to search whether there is these 2 is a member of that. It is a search array. Just imagine this is an array and this is something I want to search in the array. In normal computer, how we would do? We first go and check whether this is same at 1, 0. No. This is same as 1, 0. No. This is same as 1, 0. Yes. Okay. Match found. That's how a normal computer works, right? In the quantum computer, things happens in a completely different way, because it is a quantum register and this same register holds all the possible value. It holds, sometimes the same thing is 0, 1, the same time it is 1, 0, same times it is 1, 1, same times it is 0, 0. It is the same quantum bit. Now here we were searching it sequentially. This is no, this is no, this is yes. Okay, done, found. Here, if we have a filter for 1, 0, like just imagine there is a filter for XOR 1, 0. If we can do that, since this 2-bit or 2 position actually holds all the 4 numbers together, it actually in one single shot or on one single clock cycle, it will say whether this 10 exists here or not, because one of the answer here is if I do an XOR, here the answer will be 1 1. Here the answer will be 0 1. Here the answer will be 1 0. Here the answer will be 0 0. And if we have a filter for 0 0, if we can create a filter for 0 0, this particular bit position. If we can filter, we have a filter. Then immediately in one single clock cycle, it says yes, this particular number or this XOR is there. So everything, all these four things are there. 1 1 1 0 0 1. Everything was there inside one single register. And if we want to search whether 10 is there or not, we have to create a filter for 10, and it will actually filters out 10 from these quantum superpositions or this quantum state. From this quantum state, it actually creates 10 is, if it is there, it will the filter out. If it is not there, it will not be filtered out.
But why 10 is being repeated like in quantum register?
Oh, sorry,
I see.
it's not. It's my mistake. It's not quantum mistake.
Okay, okay.
It is my mistake.
So we are saving here 2 CPU clock cycles in quantum.
Actually, 4 CPU clock cycle, because we do not know that where this 10 will be located. So it is order of n. If there are n number, it is always order of n. But if it is n number and we have a significantly big computer quantum register, then it will be order of 1. It's just single clock cycle. It will find out whether 10 is there or not. For that, all we need to do is create a filter for that. Got it?
And how to do that means how that filter would be created then?
Yes, that's the point. That is the toughest part for a computer, quantum computer. And that is not everybody does or everybody can, and that is not anybody can. All the algorithms that we have, we really cannot convert them into quantum computers. So there comes the myth. Quantum computer is not only a very efficient and very powerful computer. It's not like that. It is completely different thing. For that, it requires completely different algorithm, and for that, the way it works is completely different. It sounds very magical that it will work. It will process all the possible number. If it is a two bit computer, it will process all the four numbers together. Sounds good. Perfectly sounds good. To uh, every number of 2 bit, it will process in one single go. But for that, we have to create a different type of algorithm. We have to create a different type of filter. The filter is nothing but another algorithm. If we can create a filter, we are done. We can do that. We can run that in any quantum computer. But how to create this filter is actually the algorithm. So here, actually, there is a gate for quantum OR, QOR. And using the QOR, we can find a particular number or not. You can try it out in IBM quantum.
Yeah, they provide online also.
Here is a simulator. You can use the simulator.
Yeah, yeah.
So in quantum level, there are different. Now all our computers, all our algorithm is dependent on few logical operators, right? Like NOT, like OR, and everything. Whatever we are writing as a program, as an algorithm, is nothing but converting the. We are doing all these things, but at the end of the day, we know how to convert those algorithms in a form of this OR and NOT, XOR, or all these gates. Because In the computer, in the chip level, in the hardware level, it is nothing but few of these logical gates. It is all the algorithms we have to convert that into form of logical gates. And for that we have compilers, for that we have microprocessor design and algorithm things, stuffs and all. All these things are there. We can write a code and it will be converted, it gets converted into in a form of this kind of gates, right? That's how it happens in our normal computer. All the biggest programming, even the Google search algorithm is also converted into this no and or not gate. It has to be done. That's how our computer works. Similarly, in the quantum world, there are different type of gates. In fact, there is something called the Hadamard gate, which is completely different than this, because this is working with four different. If it is a 2-bit of computer, it is working with four different bits, like four different numbers together. So we need a Hadamard gate which actually gives the equal probability of everything. That means if you apply a qubit and if you apply a Hadamard gate on that, any qubit enters, it gives an equal probability, like 50% probability of being 0 and 50% probability of being 1. Okay. This is what a Hadamard gate does. It actually distributes it changes the probability distribution of a qubit. It gives the equal distribution of a qubit. So this is called a Hadamard gate. There is the quantum OR gate. All these gates are there. And using those gates, we can create a filter, we can create different algorithms. Okay? And that creating that algorithm is really difficult, really difficult. And there are mathematical proofs that all the algorithms we have right now, they cannot be always converted to a quantum algorithm. That is, in fact, that is called an NP-hard problem. NP-hard problem means we really do not know. If we want to do that, want to know that, we have to follow an exponential number of calculations. Then only we can do that. So we do not know whether we can convert all the classical algorithm into quantum. Probably no. And we have only few quantum algorithms available as of now. People who are working, who are researching, they can come up with new quantum algorithms. In fact, that is the reason IBM has given it for free. It's very nice gate level. Okay, now we are fine. We understood what it is.
Yeah.
The most difficult thing, or there are so many different what is it, speculation about quantum computers. We always think when we quantum computers will comes, everything will break down, and we think that quantum computer is nothing but a supercomputer. It is a supercomputer, but the answer is not. Even there are a lot of classical algorithms which works well for our classical computer, and they are stupidly slow in a quantum computer. That happens. There are even just simple addition. Just you are adding two numbers. If you add them up in a normal computer, it will be always much faster than a quantum computer. Much faster and much cheaper. But there are few of the algorithms, few of the things that our normal computer does very slowly, but quantum computer can do it very fast. There are few of the things. And for that also, we have to create that quantum filter. We have to create that quantum algorithm. Not only that, we have to create that significantly big quantum computer to process that. Right? We have that level of very costly hardware we need, first of all. Secondly, we need the algorithm for that. Somebody will have to create the algorithm, and then somebody will have to create the filter. And after that, only we can implement that in the quantum computer. And even we implement that, few of the things that we do on our normal computer will be much faster. Even we have a very good quantum computer. But few of the things will be crazily fast in a quantum computer that we cannot even imagine in a traditional computer. Got it? Now, just to recap what we learned here in my screen, there is a classical bit is either 0 or 1, which is either red or blue. In the quantum level, it is both red and both blue, and we can only find out what is the probability of that bit to be 0 and what is the probability of the bit to be 1. And we write that in this notation, alpha is the probability of the qubit to be 0 and beta, the probability of the qubit to be 1. Okay. That is how we represent a qubit. Qubit means it is both 0 and both 1. This is alpha times there is an alpha probability of this being 0 and there is a beta probability of this being 1. Now, if we have a filter for alpha, if we have an alpha filter, we will get the 0. If we have a beta filter, we will get the 1. If it is a 2 bit, now this is for 1 bit. If it is a 2 bit, it is alpha times 0, 0, beta times 0, 1, gamma times 1, 0, and delta times 1, 1. Okay. And a single register will work all these, will process all these bit positions together. Searching some particular number is super easy. If it is 3 bit, it is alpha, beta, gamma, theta, delta, epsilon, psi, beta, theta, all these things you can all the Greek letters we know we can add it up and we can create more and more bits. But in reality, it is not only the Greek alphabet that matters. What matters is creating that big quantum computer is so costly. Quantum computer operates in almost sub-zero Kelvin, like almost 0 Kelvin temperature. That means the coolest place on the earth. Only on those places we can run a quantum computer. It actually requires the particles, or it actually requires those metals to work in almost in the absolute zero temperature. Absolute zero temperature we cannot achieve on this earth. So it is almost the absolute zero, almost near to 0 Kelvin temperature. We have to bring the entire system into, and then only those particles will show some quantum traits on that. Otherwise, it will be a classical physics we can do. But if we want to make it a quantum, we have to, if we want those particles to show some quantum traits, or it will show the quantum nature, in that case we have to bring them down into almost the absolute zero temperature. And bringing anything into absolute zero temperature is crazily costly. Cannot do that. Okay. So that's why it's super duper costly. That's why it's not only just some bits we can simply add on bits, but it does, we can do that in the classical computer, but in quantum computer, for every bit we have to create a system which goes to that absolute temperature. That's crazy costly. And now we know how to represent a qubit, how a qubit works, and all we need is a filter and an algorithm. A quantum algorithm is totally different than a classical algorithm, and it also requires a filter. Perfect. And this is every quantum bit is a superposition of 0 and 1. We can only filter out if we know that filter. In the public key cryptography, we remember all these everything is dependent on a trapdoor function. If you remember RSA, it is dependent on a trapdoor function. What is that trapdoor function? Multiplication is easy. If we multiply two very big prime number, it's easy to find this number. A normal classical computer can do it very easily. But given this big number, we really cannot find what are the factors for this number. What are the two numbers that being multiplied gives this number? If these two numbers are prime, that means there is only two numbers for this, but there is no other combination that will give you this particular number. But finding that two number is very, 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 very difficult for a computer, classical computer. But in quantum, the encryption is easy. We can simply multiply that, and code breaking is also easy because factorization is also very easy in a quantum computer. Peter Shor is a mathematician who has given an algorithm that actually works in a quantum computer, and it gives this factorization. It gives the factorization of this big number into two prime factor or whatever factors are there. It gives all the factors of a number, and it can work in a quantum it is a quantum algorithm. In fact, this is one of the first quantum algorithms that came in. And this algorithm, how it works, going into that is little bit difficult, I guess. We need a few more understanding on how exactly Peter's algorithm is working, Shor's algorithm is working. So he says, okay, one more thing I just need to explain, just in case you come up with this particular picture. This is called a Bloch sphere. That means this position, this small dot is the position of a bit or an electron or any quantum particle. This is the position, and we represent it in a three-dimensional space. We could have represented it in two-dimension also, but we created another dimension just to represent the imaginary numbers. So it might have some imaginary location as well. I'm not going detail into that imaginary location. If you remember, there is something called A plus IB. That is something we have written y equals to A plus IB. I is square root of -1. This is an imaginary number. So to create some space of the imaginary space, because there are few spaces where electrons are there, but we really don't, that those are imaginary space. Those doesn't exist in reality, but electron can go in those spaces also. I really don't want you guys to be mad by the end of this day of the day. So I'm just skipping all these things. But in case you come up with this picture, with this is the representation of a quantum particle or quantum bit, and this representation is called Bloch sphere. Bloch. This is this is called Bloch sphere, and this is how we represent a quantum bit. Now let us come to Shor's algorithm. Shor's algorithm. Again, not going very deep into that. Let me know if you are feeling that you are going mad, or if you are already feeling. Shor's algorithm says if there is a number, we need to find the factor of A. That is very difficult for a normal computer. Shor given an algorithm. What is that? Shor given an algorithm, A factor, to find A factorial, we find another number called R, so that for R -1 is sorry. She says we have to find a number R so that we can represent that into this form. A minus R -1, sorry, A power R -1 equals to this thing. This is a formula we all know. A square -1 equals to a simple mathematics formula. You remember? A square -1 equals to a plus 1 into a minus 1. Do you remember this formula?
Yes.
So this gave something to in Peter Shaw's mind. He thought, okay, cannot, if I want to find a factor for a square minus 1, then this is actually a two factors. We need to find this square. If we can make a square root of a number, we can easily find the factor because this is a factor, this will be another factor. So, but everything cannot be expressed as a square root. For every number, we do not have a square root, but we can have any other root, right? That's why he says if it is r by 2 is actually square root of a power r, right? R by 2 means what? Square root of a by a power r. So he used the same formula here. Just see a square to a, that is square root of this number. This is also square root of this a power r, and this is also square root of a power r plus minus 1. So these will be the two factors of this number. What he says, using this formula, he says, let us try to find out the factor of 15. What he says, all you have to do, you have to find all the possible, you have to take any random number, just take any random number 0 to 15, which is not a co-prime to 15, that it doesn't share any common factor with 15. And secondly, it should not be even. It should be even. It should not be odd. Just give me any number. Anybody just give me any number which is less than 15, which is even, and which is not divisible. 15 is divisible by, which is not having a factor with 15. Any number.
4, 4.
4. Okay. In this table, just see here is 4. 4 power 2 minus, if you just, this is the formula. You just create a GCD of that number 15, 4 power 2 minus 1 and 4 power 2 plus 1. So it will 4 power 2 square root of 4 square. That means 4 minus 1. It is 3. 15 GCD. If you create the GCD, it will 3. And same GCD of 15 and 4 plus 1, 5. So it will give you the 3 and 5, which is the factor of 15. Just take any other possible number which is even and which is not co-prime to 15. You will find, if you just apply this formula, all you have to do is two simple GCD. You have to find the GCD with this and GCD with this. You will find the factors. It is 3 5 3 5 5 3 3 5 1 5. All possible. Any, irrespective of the number you have chosen, any random number you just take which holds holds that property with 50, and you will find a R. You can find a R for which you will get this GCD, and just giving this GCD, it will give you the factors. It's that easy. But it is very difficult for our traditional computer to compute it. Why? Because you have to find this R. How you can find this? Here we have a table. We could find, okay, this is the R. This R will hold good. But you have to find a R. If you can find this R, if you are lucky enough, you can simply find the factors. But finding the R is more difficult than actually factorizing the number in traditional computer. But Shor has created a famous logic gate, and that logic gate gives you an exact filter by which you can filter out this R from a given set of number, because all the possible numbers are there in a quantum register, and there is a filter which will filter out this R for a given A. The moment that algorithm is given by Peter Shaw, our RSA cryptography is broken, because it's super easy now. Anybody can do that. Fine. This is where quantum cryptography starts. Now, so far we started with quantum physics, then we went to quantum computers. So far we are talking about the quantum computers. Now with this Peter Shor's algorithm or the Shor's algorithm, it has proved, mathematically proved, that if we have a good quantum computer, the RSA, breaking RSA is nothing. It will take just a few moments. Even within one single clock cycle, we can break the RSA crypto system. Right? Now comes
Yeah.
quantum cryptography. Okay. So it is not a problem that we have a bigger computational power. Again, I'm telling this is a myth. This is a very big myth that quantum computer will be more powerful. It might not be more powerful, but some of the algorithms can be processed very quickly. Not all. We still need supercomputer to do it faster to make some faster computation. Quantum computation is not going to replace a traditional computer because that works with completely different algorithms. What we need, the problem, we are increasing the key size of RSA not because of there is a quantum computer, or there are, in fact, there are many research articles I have read which claims that bigger the key size, it will be resilient to the quantum computer. The answer is no, it will not be resilient to quantum computer. We are increasing the key size. We are increasing the key size from 2048 to 4096 bit in RSA, not because of quantum computer, but because we are achieving more and more computational power in our traditional computer. We are going to have more cluster computer. We are going to have more supercomputers, and those are there, and those are bigger threat than quantum computers. So those computers are already there, which is which is super fast, which can actually process a 2048 bit key, which can factor it in a span of say 2 days, 3 days, or 10 days. That's why we need 4096 bits. So again, it become almost 10 years for any supercomputer. But still, if we just connect all the supercomputer in the world and we can make a cluster computer of supercomputer, the RSA crypto system will be broken. But this is a theoretical threat. If we can have a quantum computer, does not matter what is the key size of the RSA, it will be broken. The trapdoor function itself is broken. It is not about the key size. We cannot fix it by increasing the key size. So we increase key size for a different reason, which is we are having more computational power. But we are thinking about post-quantum cryptography because we need some better algorithm for quantum cryptography. We need some better algorithm or better trapdoor function that quantum cryptography cannot break. And there is no way we can create a filter to break that quantum algorithm. So that is a different problem set, and this is a different problem set. And most of the cases, in fact, if I'm not wrong, 99.99% of the professionals, security professionals, always think that quantum computer is replacing the normal computer, and due to the quantum computer, we can simply keep on increasing the key size. But it's not going to happen. We need to increase the key size because of a different reason. Got it? So when I said that every time I was telling that if we have a good quantum computer, now we have good quantum computer, IBM is super excited, Google is super excited. There are another quantum computer has come up in China, Taiwan. I shouldn't say China, Taiwan. It has come in Taiwan, and for this, all these people are very excited that hey, we have achieved a supercomputer and we can use the Shor's algorithm in that. But do you know this IBM supercomputer that we are so excited about? What is the biggest number that it could factorize using Shor's algorithm? Any guess? The number is 21. 3 into 7. That is the biggest number the IBM quantum computer could factorize till date. There are other quantum computers, using Shor's algorithm. And there are some other algorithm, which is a modification of the Shor's algorithm using that, not IBM, not Google, but all the quantum computers that we have in this world right now. This is the biggest number that we have achieved to factorize. This is the So do you think this is a threat for us at least now? Using the quantum computer, IBM
No.
quantum computer, this is the
Till
number.
the time algorithm is built, no threat.
Till the time the algorithm is built, till the time we have a good quantum computers. And anyway, this is few guys claim that this is the number they have factorized. This is if their claim is right, we do not know whether this is right or wrong. There is no evidence yet. People are trying to figure out. If we figure out, then this is probably the largest number till date, what we could factorize using some good algorithm in quantum computers, whatever quantum computers we have. So this is yet not a threat for us. So just be assured we can keep on using our RSA, we can keep on using our ECC. We should use ECC over RSA not because of quantum computer, but because of we have a bigger computational power right now. Any normal computer can break RSA nowadays if the key size is not significantly big. And 4096, yes, it is still unbreakable because our normal computer cannot break, nor even the quantum computer. But 4096 bit is very big, right? It's 4996 bit just for the key size. It is too a big information to carry. So that's why 4096 is not scalable. After that, if we come up with some 8192 bit, so if we come up with that, so that will be very big. So RSA will might not be scalable. In fact, by the time will have a quantum computer to break an RSA algorithm, we will probably abandon RSA algorithm. It will be deprecated by then. Because by the time the amount of the length of the key will be so big, we cannot use RSA. So quantum cryptography, in my opinion, is not a threat for RSA. RSA anyway will be deprecated because of the bigger key size. Got it? ECC is a better way to go. ECC, because ECC with that smaller key size, we can provide better security. For RSA, what we for the same level of security we need 4096 bit, but here it is 256 bit of ECC keys enough to provide the same security for 4096 bit in RSA. So ECC might be the one, and probably when this quantum computer will come into the picture, we need another algorithm to break ECC, another filter to break ECC, which we do not have right now. And we do not know who will come up with that idea. Peter Shaw came with the idea, and that is the path breaking thing. And again, somebody will have to come up with a new algorithm, because this kind of algorithm, the way he thought, is a different way. Because who do all these nonsense when we know that factorization is easier than doing this? But he found some better way to do that at a quantum level. Similarly, somebody else need to find a better way to break the ECC. Then we have to implement that into a quantum computer. Then the ECC algorithm is on stake. RSA is on stake, but not for quantum. Clear enough?
Yeah.
Here is a theorem that when these quantum computers are will be a threat for us. Yes, it is a threat for RSA. It is a threat for DSA, Diffie-Hellman. ECDH is threat or not threat, I do not know. Let's see. Yes, this is elliptic curve Diffie-Hellman. This is elliptic curve DSA algorithm. All these things. Yes, since any algorithm we have that uses trapdoor function for the cryptography or for doing encryption, that is on stake, but we do not know whether most likely we do not have any algorithm at all to do that. And if these things are on stake, then TLS, SSL, all these digital signature, digital certificate, blockchain, everything will be on stake. And if they are on stake, we know what will happen. All the banking system will collapse, all the cloud computing will collapse, all the IoT system will collapse, blockchain will collapse, all these things. But those are good as a fairy tale, those are good as a scary movie or the horror movie. But in reality, the theory is x plus y is greater than z. then we need to worry. What is this X and Y? Security shelf life is X. That is how many years this RSA algorithm will be there. That is what we are calling X, and how we need to retool the existing infrastructure. If today RSA is broken, how many times we need to replace RSA with something? ECC, elliptic curve cryptography, is nowadays coming, but this is not a de facto standard, but it is a recommended standard. And it took almost 6 years, 5 to 6 years to replace RSA with ECC. Not replace, but yes, to make ECC more popular than RSA. It took almost 5 to 6 years. Now, if we just think that we need to replace RSA with ECC, probably we will need more 3 to 4 years, or maybe 5, 6 years more to completely replace the RSA. And in that case, that number of year is called Y, and X is the shelf life, or how many years this particular algorithm will stay. If these two are greater than the quantum algorithm, the quantum code breaking time, then it's fine. Like how long, not quantum code breaking time, how long we need to build a quantum computer. Right now, I don't think, like, there are many people have many speculations. Let us come to this. In 96, somebody said it will take 20 years. 20 years, no, we couldn't achieve it. Microsoft research in 2015 said that it will another decade. So it is 2025. I don't think that is a very good, that timeline we can come up. Because it's crazily costly. For every bit, you have to create a absolute zero day person. It's only this particular condition will make it delay, will be super costly for us. And at the same time, NIST, somebody in the NIST and Isaka said that there is 1/7 chance of breaking RSA 2048 by 202. So this guy probably spoke in a quantum level language. It's a probabilistic language. He says half chance by. So he said that 2048-bit RSA will be broken by a quantum computer, by a real quantum computer by 23rd with 50% chance. That I believe that is a quite a fair assumption. And the same guy said it will 1/6 chance within next 10 years in 2017. But still, I don't think by 2027 we can build that big quantum computer. And even though we have the quantum computer, we do not have the algorithm. RSA, yes, we have Peter Shor's algorithm. Shor's algorithm is already there. But for ECC and others, we do not have the algorithm. We need to have the algorithm also, not only the machine. We have the machine, but we do not know how to run that machine for breaking other codes. So that is a problem. So it is. In my opinion, it is really not a very big threat if we are we are diligent enough to replace the RSA, like not RSA, replace the cryptographic protocols or the cipher suits. If we replace it time to time, and we are quite diligent to do that, I don't think quantum cryptography will be a problem, because for everything we need a new quantum algorithm, and that is not going to come very soon. And probably the way today's computer is working, if we really want a quantum computer to work in that way, that whatever we write, there is some other compilers, compilers, quantum interpreters to come. I don't think that will happen in the next 30, 40 years. That is my opinion. But let's see. We'll see the future, and we'll find what is happening. But just don't get scared by not knowing this. These are the facts. These are the numbers. This is how it works. This is there is a bottleneck for quantum computers, and that bottleneck will save us at least for the coming 10, 15 years. That I am pretty sure. And we are also working on different type of post-quantum cryptography, how we can do this cryptography, what kind of cryptography would be good. Like ECC with 256-bit is why we are calling it quantum resilient, because we do not know the algorithm. Even though tomorrow we have a very good quantum computer. So that is why many of us are pushing towards this elliptic curve cryptography. And we are pushing it not only for the quantum. Again, the another reason is it's for RSA right now we have a very crazily big key size. We don't want that. Okay. Now there is one more thing I just want to cover in the next 15 minutes, maybe. Yeah, 20 minutes I have. I'm going to cover one interesting thing and then we'll take a small break. Okay. This is something what we discussed about quantum cryptography, how the quantum code breaking will happen, how it can destroy the entire quantum world and all. This is another interesting thing I just want to share with you. The quantum cryptography, if it comes, the quantum computers, if it comes, it does not only break the existing existing cryptography or existing encryption technology, but also it has a potential to create a new cryptographic suite or create a new encryption technique, which will be super strong, which will be even stronger for the quantum computers. Even a quantum computer cannot guess that. Quantum computer can come up with a better way of doing encryption. So that is another part. So this positive part, very few people says, if quantum computer can break up cryptographic algorithm, it can create cryptographic algorithm as well. And I am sharing a very simple one, which is called a quantum key distribution network. And in fact, this is being used. Beijing Shanghai backbone is there. It's used by China for the quantum key distribution. This is a Swiss quantum network. They also use the same thing. They use photons and they use this what the fiber net network, and they distribute. There is a very nice quantum key distribution algorithm, and they use this algorithm for quantum key distribution. For key distribution, we know another algorithm. What is that? How we can distribute the key? We have an algorithm.
Diffie-Hellman.
Yes, exactly. Diffie-Hellman. Now, Diffie-Hellman, we have a stronger algorithm with quantum computers, which can actually is much stronger than Diffie-Hellman. In fact, if we have this one, we do not need a private key cryptography. We need private key or asymmetric key cryptography. It is such a better way to distribute the keys. We might not need that one. What is that? By the way, this is actually the Shor's algorithm representation using the gate. This is the gate that Shor used for his algorithm, the filter. Okay, Alice and Bob, they are two guys and they want to share a secret key among themselves. That's the problem definition. And if there is a quantum channel, they can do it. Okay, another interesting thing, probably again it will blow your mind just for an information for you. It might sound very interesting. For quantum, there is one more thing called quantum entanglement. That means if two electrons comes in contact and they have some quantum exchange, after that, does not matter how far they are, they might be some light years apart, still one electron will have effect on the another electron, or one quantum particle will have effect on the another quantum particle. That means two quantum particles collide. So there is some exchange of momentum, there is a exchange of force, there is exchange of lot of things. The wave distorts, all these things happen. And now just imagine these two particles drift apart by a light years or 1,000 light years. Still, if there is one single, like one of those quantum particles gets another agitation, or it just starts moving, the other particle will also feel something, the other particle also starts moving, or other particle will also get some information from that. That is crazy. It is called quantum entanglement. Once you have a quantum collision between two quantum particles, that will always be there. That effect will always be there. So they will somehow will be interlinked. And this is called quantum channel or quantum tunnel. And this is the basic of teleportation. You have heard this term teleportation?
No.
Teleportation means I can sense anything, anybody, a human being or an animal or any object from one place to another place in form of energy. That means just imagine E equals to mc square. We all know Einstein's famous formula. Just I have a pen. I am holding a pen. How about if I know a way so that I can convert this object, this mass into energy,
Okay.
and send that energy to some other place, and then again from that energy we can get this pen back. In that case, this pen will travel from my table to somewhere else without any physical mode of transportation.
Yeah.
Right?
I misheard. Yeah, I misheard the term. We know this. Yeah.
Yeah, teleportation. It is a famous. Like anybody has watched any sci-fi movie or any sci-fi story, teleportation is used.
Mhm. Yeah. Yeah.
And using quantum channel or one quantum tunnel, you can actually teleport any object in light years ahead. Because if we just simply think about energy, we convert it into light. In that case, the light has a speed. Light years means the light will take 1 year to travel that. But if we have a quantum channel, since these two electrons are always like once they have collided and then they were drift apart, but still they have effect on each other, that means there is some way by using the quantum channel or the quantum tunnel that the information or energy travels faster than light, in fact, much faster than light. And using that tunnel, we can send any object to anywhere in this entire universe in even faster, much faster speed than the speed than that of light. Maybe some 1 million times faster than a light. Yes, if it is a 1 million light year ahead, and we have a good quantum channel or quantum tunnel, we can actually send something from here to another that 1,000 light year ahead planet in just in a fraction of second. So we can do that. So this is not really sci-fi. In fact, IBM TJ Watson lab is working on that. They are working on quantum teleportation. In fact, they claim that they could able to send a hydrogen atom from one place to another place using quantum channel. And if we can really do that for anything, and if we know that how to convert a mass into energy and back energy to mass, probably we can travel anywhere in this entire universe. We do not have any limit, any physical limit we will have. We can travel anywhere. So it sounds much more fiction than the fiction, but this is reality. This is theoretically reality, but not practical reality. Practical, we do not know when we can achieve that. But yes, people are working on this quantum channel, and in that case, soon we can see something called quantum network, which will be faster than our for this this optical network, network. Because this will also optical network will also travel in the speed of light, but yes, people are also working on the using the quantum channel or the quantum tunnel for building a network where any information can travel much faster than light. So that also we can see very soon. Probably nowadays we don't hear that, but yes, there are few people, few scientists in silos. They are working it in silos, but maybe very soon we'll see. We'll hear about the quantum network as well. Sounds interesting.
Yeah.
Okay. And I do not hear from anybody else, guys. Just can you make a noise for me?
Yes, sir. Sorry, construction is going on. So if I
Oh,
unmute it, there's a lot of sound that's coming in.
okay, no problem. Okay, but
So,
you
but
guys,
how, if you go to the previous slide, how they, so how Beijing, Shanghai
yeah,
exchange
this
the
is
key?
not quantum network. This is just exchanging of key. I'm coming to that. Yes. So for this
Okay.
polarizer part, we understood. Now there are different spin of the electron, and if we have a good filter, we can filter out this electron. So this is a polarization. So a polarization in a particular direction, it actually filters out so that our eyes doesn't get irritated. Right? This is a polarization. This is our wave works. Okay. Just imagine there are photon or any quantum particle, and it mm, okay. So a photon can have different spin, either this one or this one or this one or this one, or there are thousand others. But for the time being, let us take there are only four type of spins. Rest of the spins we are not considering. We will not consider those probability. Only the spins electron have a spin like this, like this, like this, or like this. And if we want a filter for this is not the actual filter, but we are representing the filter. Either the filter would look like a plus or the filter will look like a cross. A plus filter will filter out these two, and a cross filter will filter out these two. Okay, this is more of a logical representation, not the actual representation. In actually, the filter does not look like this. Logically, we are thinking if the electron is moving this rotation, or either this as this spin or this spin, we just need a filter which would logically look like this. So this filter will so this spin will pass from this, and this spin will pass from this. Or if it, I think this, and this is a class filter which will pass from here or here. This one. Just like this, and this is a plus filter, this is a minus filter. And electron has this kind of spin. Either this one, this is one, this is zero. This is one, this is zero. 1, 0. This is also one. This is also sorry. This upward is one, downward is zero. Or if it is rightward, it is one, and leftward is zero. And we have different filters for doing that. And now Alice is sending something to Bob. Alice needs to know which kind of spin she will send. So for that, she needs a sending filter, or she needs to filter out a particular spin. Like either zero can be represented by this one or by this one, right? This two will be zero. Either this one is zero or this one is zero. Alice can create either plus filter or cross filter to send a zero. Similarly, she might need the plus filter or cross filter to send a zero. And in the receiving end, Bob needs to know the exact same filter that Alice has sent, then only he will get the exact data that Alice has sent. Otherwise, he will get a distorted data. If she tries to use a cross filter for a plus, like for this kind of spin, he will get a different answer. Or for this kind of spin, if he uses a cross filter, he will get a different answer. Either zero or one, some random probabilistic answer he will get. But if the sending filter and the receiving filter are same, then only they will get the same bit, right? Either 0 or 1. You are with me? It's clear?
Yes.
Okay. Now the beauty of this algorithm, the how this key distribution work, either we have vertical or diagonal. Right now we are taking a photon and it has either a vertical or a diagonal way. Vertically, if it is, okay, previously I just told you that either upward or downward. Now in this example they have taken a different, like either horizontal or vertical. If it is vertical 1, horizontal 0. And if it is right slant or right side for plus 45, then it is 1, minus 45 means it is 0. That's how they have taken the polarizer filter. We can take any other type of polarization filter. It is more of a how we are logically representing it. Now this kind of filter Alice is using to send, say Alice send 1. One might be this one or this one. The first one, Alice used this filter to send 1. The second one, Alice needs this filter, the blue filter. The third one also this filter. So randomly Alice takes the filter to send zeros and 1 and it reaches Bob. Now the first one, Bob uses the other filter. So this is a cross filter, diagonal filter, but Bob takes it randomly. He uses a horizontal filter. So he will get a different answer. Again, this one, Alice sends some 1, and here Alice's filter and Bob's filter are same. Bob doesn't know. Alice also doesn't know that what filter he is. Bob is using some random filter, and Bob will get some answer. All these things, 0, 1, 0, 1, some answers he will get. Now, whatever Bob gets, he sends it back to Alice and says, "Hey, whatever you send, I got this sequence I got." What Alice will do? Alice will find what she sent and what Bob got, and from this information, Alice will found what is the sequence of the filters that Bob has used. Like Alice sent 0, Bob gets 1. That means Bob has used a different filter. Alice sent 1, Bob gets 1. That means they have used the same filter. This is how Alice and Bob, the moment this Alice has sent some random filter, used a random filter, Bob has used random filter, but whatever Bob got, some different number, he send it back to Alice, and Alice immediately will understand, okay, no problem. This is the sequence of the filter you use. But no eavesdropper cannot use that. We cannot do that because they neither know what Alice has used nor what Bob has used. So they cannot find. So you have to know either what Alice has sent and what Alice has used. These two information you need. These two information is with Alice. That's why Alice knows that whether my filter is matches with Bob's filter. If it matches, fine. If it doesn't match, she can change her filter. This is what a key distribution. This is how the quantum key distribution happens. So this is much better than Diffie-Hellman. There is no trapdoor. It's just random. If it is a quite big key sequence, it is just a random. Like it is almost unbreakable. And this is used. Not even the guys who use this thing, quantum computer to do that. This is a quantum. They just need a quantum filter which say if we have polarizer sunglasses which we can afford, these guys can afford a better polarizer filter, and using that polarizer filter, this is the concept of quantum cryptography. They implemented that quantum cryptography using photon and polarizer, the same polarizer that we are using, but of course a better one which can actually filter out different ways in different ways. So so this is concept of the quantum cryptography, and they implemented the concept using some normal things like some well-known stuff like polarizer filter and photons, and they just implemented it. They did not need a quantum computer to implement that. So this is widely used. This kind of key exchange protocol is widely used. many places we are using, and this algorithm was given by Bennett and Bressard in 1984. And this is called BB84 protocol, which is kind of a standard now. NIST standard is there, and using the same thing, we can using these filters, we can actually find out whether it how we can actually share the keys. We can share the same filters. The sequence of filter are same, then fine. Nobody else cannot know the sequence of the filter, so they cannot filter out what is the data being sent. Fine. Understood, everybody?
Yeah, but in quantum, qubit is there. So for each register has all the values, no?
Yes, it is all the value. Even for the photonons, it has all possible direction. It has all possible. It has a spin in all possible directions. Here we are not using qubit directly, because using qubit and processing qubit, you need a quantum computer. But this protocol does not need a quantum computer.
Okay. So this is not on quantum computer.
This is not quantum computer, but this is the concept of quantum computer.
Concept is used.
Yeah, they have
Okay,
used.
so now
Yeah.
in this example, we have a shared secret key 0101. So now the data exchange will happen on normal AES or whatever symmetric encryption.
Okay, one more good thing. AES or DES algorithm, what we have learned, are they quantum resilient or not? What are your opinion? Do you think that quantum cryptography can break AES or DES anytime?
I don't think so.
Why?
They will not able to break.
Why?
Algorithm?
Yes, but algorithm is not there. But there is one more reason for which it is almost unbreakable. Do you know that? The reason is AES and DES uses Shannon's theory of confusion and diffusion. Shannon mathematically proved that if you have enough way to make this confusion and diffusion, this code is unbreakable. You cannot get the previous thing back. If you have significant amount of confusion and diffusion infused in your data. And AES and DES does the exact same thing. AES uses P box and S box for creating that confusion and diffusion, and DES uses Fistel cipher to use the confusion and diffusion. You remember those classes that we have gone through all these things, right?
Yes,
So this
yes.
confusion and diffusion theory that Shannon has given, that is mathematically proven, and mathematically proven in the quantum world also. This mathematics will hold good. Mathematics doesn't have any problem with quantum. Only the physical laws have some problem with the quantum.
Correct. But for AES, 256-bit key is required, right? So I don't miss how the shared secret key will come 256 bits. Means this
Sorry?
is only 4-bit. In this example,
Yeah,
the
now it is 2. In fact, it is more than that. I think 512 bit is used for the in reality in BB84.
but here our key size is only 4-bit, no?
In this example,
Yes.
why 4 bit? Okay, you are thinking that only 4 possible way to filter out, right? But this is not important. This is one way, and the sequence of the filter is
No,
also.
the step 7. After this all lot of steps, we came up with the secret key that they'll encrypt the data, and Bob will decrypt the data.
Yes, yes.
So that is 4-bit only.
Because I have taken an example with 8 bit only, na? I have taken a smaller example. I like if I have 5, like here I have taken a smaller example. That's all. This is for our example only. But in reality, it is 512 bit key.
Means nobody will able to say correctly how many bit will come in the secret key. It will vary.
It will not vary. It will 512. The polarization, the sequence of the polarization filter is used is 512. The input string, like the data might be any number of bit, but the filter sequence will be repeated. Like every 512 sequence, like every 512 sequence of the filter will repeat one again. 512 is done again.
Okay, so they'll keep repeating the process till the time 512 bit come.
Exactly.
Okay. Then it is fine.
Yeah, I have taken a smaller example. You have to explain the thing. That's all.
Got it.
Okay. And yes, post-quantum crypto replace the traditional public key cryptography. This is very important. Everywhere, when we are writing, we say it is public key cryptography, not private key cryptography or symmetric key cryptography. So symmetric key cryptography is absolutely fine and it is already quantum resilient. Now, if we have a better some crazy guy come with a crazy algorithm that is going to break the S box and P box, then we need to create a better cipher. That's all. But theoretically, the symmetric key cryptography is already quantum resilient, unless some crazy algorithm comes. And even it comes, we can quickly change the cipher. That's not a very big problem. But it is a threat for the public key cryptography is because that is a trapdoor function. And we have different people working on that. They are working in different direction. A lot of new things are coming, and maybe we do not know. Maybe tomorrow some new invention or new discovery will make the entire thing faster. So that's why all the companies, even in the executive order that recently came in, there also, and many of the nations cybersecurity framework are also mandating everybody to come into quantum resilient or quantum agile methods. That means these two what you will listen in your office or in your company wherever you are working. If not today, maybe in 1 year or maximum 1.5 year down the line, you will hear this term. One is quantum resilient and one is quantum agility. That means all our protocols, whatever we are using, we should be agile enough to adapt any quantum protocol that comes in future. That is because nowadays there is no point of investing money to create post-quantum cryptographic or quantum resilient cryptography by the companies. Let the poor researchers in the academia do their job. Industry is not going to invest a lot of money. Yes, of course, IBM, Google, who are doing research. It's for the research, not for the implementation, not for the business. But what the business want to be quantum agile, or the quantum agility is the term which is widely being used nowadays, so that we will use our system, we will create our system in such a way, anytime we require a better cryptographic algorithm or a quantum cryptographic algorithm, we should be agile enough to adapt that. So that is the mandatory, that is the mandate, or that is most of the companies nowadays thinking. In fact, in Dell, I can say we are already working on that for last 6 months or so. In fact, yeah, there is a group formed and for this quantum agility. In fact, if you go to SafeCode is a very good forum or organization that is a consortium of many companies for the security practitioners. And in SafeCode also there are a lot of good documents about this quantum agility and all. You can find few papers there. In fact, few of them are written by me as well. You can, if you have enough time to waste, you can read them. Okay.
Mhm. Okay.
Now let us take a 5 minutes break and then today you have a session at 1:30, right? For your for some career counseling or
It's
something.
at 1 o'clock.
It's at 1 o'clock.
Yeah, 1 to 1:30.
Okay, then let us take another 15 minutes and take the break at 12:30. Will that be better?
Yeah, we could do that.
For 12:30 for lunch.
Yes, because you guys have a session at 1 to 1:30. That's what Pranav is saying.
We'll take lunch break 1:30 to 2:30 is my opinion.
Okay. 1:30 to 2:30. Okay,
Because
fine.
lunch has to be ready, no?
Okay, lunch has to be ready. But 1 to 1:30 anyway, you guys are going to have a session. So that time we are anyway stopping the class. I'm just thinking that so you will have 1.5 hour of lunch break. Is that fine?
We could start at 2.
We can do 1:30 to 2:15,
Yeah,
whichever way
2:15.
everybody says.
Then
And
let's take a
we will take one 10 minutes break, sir.
Yeah, let's take a 10-minute break because quantum is too heavy for all of us.
Yeah.
We know. So let's
Thank
take
you, sir.
a small break for 10 minutes and then we'll come back at 12. What is the time now? 12:09. So 12:20 will come and we will we'll see some lighter things, not this much of not something like quantum or cryptography, anything like that. It's we'll discuss something lighter. Either IoT we can discuss on, or we can okay we can discuss with IoT. No, with IoT I have a plan to do conduct a GD also. So we'll start with the modern how to secure the modern application stack. So that will be quite lighter. I will keep that quite lighter because if you guys are not doing hands-on with the modern application stack, it will not make much sense for me to go in detail or go in depth. We'll make that lighter one the next session. Okay. And after the lunch, we'll have a GD session and we'll have we'll have a session on how to secure IoT. And we'll start with that and then we'll do the GD session and then we'll again finish the IoT lecture. Okay, that's the plan for today. So let's come back at 12:20.
Sure, sir.
Okay, okay, we'll come back at 12.